All right, guys, here we go. Gonna go through the remainder of the notes, pages 3 to 5. All right. So we're gonna restart with what we ended on, page 2, that the formal definition of E, right, this transcendental number, is the limit as x approaches infinity of this ratio. Okay, so basically what I wrote right here, right? But it's a little bit counterintuitive, right? Because you would think if x gets really big, well, 1 over a really big number is 0. 1 plus 0 is 1. 1 to anything is 1. Okay, but it's not. And we'll look at that through these values, which we actually did right here. So we can actually just copy these. 1 plus 1 over x. When x raised to the x when x is 10. So, this expression when x is 10 lines up with this, etc. All right, so I'm just going to try and copy these. So 2.59, 3742, 2.704, 814. Make sure that the decimal point's clear. 2.716, 924. 10,000 is 2.718, 146. When x is 100,000, we get 2.718, 268. And then when x is a million, we get 2.718, 280. So an estimate for E is about, what I remember. Sorry. Just want to be sure that's a nice clear decimal point. And this is 2. So roughly, E is about 2.71. This is just being sure that you know how to find it on the calculator, right? On the Inspire, it is 2 buttons to the left of the number 1. And I think that's what most of you guys have. Let me know if you have something else and can't find it there. All right? And the value of E to 9 decimal places is right here. So I will just draw a little arrow showing that. Okay, and like we've mentioned before, if we have continuous growth, or the idea of something compounding continuously, this is the expression that we're going to use, right? This we've done before. So I'm going to say C, end of page 2, because we just did it. 6% for 4 years, yeah. Got that right here. Okay, now if we look at exponential functions, right, with various bases, and what that means is, how do these functions change if the base goes from a 2 to a 10 to an E? Okay, the domain of these is all real numbers. You can plug in any value for x, right? X can be anything, and you can take a positive number and raise it to anything and get a result. The range is going to be y greater than 0. The asymptote is going to be y equals 0. The x-intercept, there will be none. And the y-intercept is, 1, so I'm going to write that as 0, 1. And the characteristics, right, we've done this in the last class. But if the base is greater than 1, the graph goes up. If the base is between 0 and 1, then the graph goes down. Okay? And then we can apply all the different transformations that we know to those. All right, last page. So, what are some examples of when we might use this in a non-financial scenario? Well, to be honest, there are a lot of them. They occur very naturally in population growth, in radioactive decay, stuff like that. So let's say, for example, you have a population that increases by 4.5% per year, right? That could be an example of where we use this function, right? The current population, excuse me, the new population is equal to the original population, the initial, times e to the constant growth rate, which in this case was 4.5%, 0.045 as a decimal, times time, right? So we could model this scenario as p, the current population, is equal to p sub 0, the initial population, to the e, or times e, to the 0.045 t, where t is time in years. Okay, if we have decay, it's this equation, right? The only thing that changes is instead of a k, we have a negative k value, right? And we also have these Newton's law of cooling and carbon-14 dating examples, right? So this is the rate at which something cools, depending on the ambient temperature of the fluid around it, right? So I is the initial temperature of the object, that's this. T is the temperature of the surroundings, so whatever fluid it's in. And remember, fluid could be air, it can be liquid, it can be gas, which I guess air is. So that goes here and here. K is a cooling rate, so this is measured by various characteristics of whatever the object is. But you take E and you raise it to that rate times the time, right? And then with carbon-14 dating, if we want to know how much carbon-14 was in a sample, we can figure out the amount that it was that it started with, right, when it died, when the carbon started decreasing, and T is the length of time. So usually the way this works is we measure how much this was, and we know in theory what the amount of carbon-14 that was supposed to have at the beginning was, and we can measure time, right? Because we usually know this depending on the substance. That's it, guys. So those are some examples of when you might use continuous growth in both finance and outside of finance. And there's a refresher here of what exponential function properties have, or what properties they do have depending on the base. And here was just again an explanation of how you determine that number e, what it really means. All right, so I will end the video there, and as always, hope these were